Welcome to Talk Tensors, the show where we really get into the leads of machine learning research.
Glad to be here.
Today, we're doing a deep dive into a paper that tackles something pretty fundamental: how AI can keep learning new things from, well, not much data.
Exactly. It's about Few-Shot Class Incremental Learning, FSCIL for short.
Right, FSCIL. And the core problem is stopping the AI from basically wiping its memory every time it learns something new.
That's the one, catastrophic forgetting. It's a huge hurdle, especially in real-world scenarios where things are constantly changing.
And this paper we're looking at today proposes an experimental approach, using those big vision language models.
Precisely. The paper is titled An Experimental Approach on Few-Shot Class Incremental Learning. It looks at an existing method, LPDI, which is already quite good.
Okay.
And asks, can we make it even better by swapping out its vision language component? Specifically, replacing CLIP with a different model, CLOB.
Interesting. Before we dive into LPDIF and CLOB, let me just step back a bit. Why is FSCIL such a hot topic right now? Where does this actually matter?
Oh, it matters a lot. Think about practical uses, like medical diagnosis.
Yeah.
You have a system that knows common diseases.
Right.
Then a new rare one pops up. You only have a few examples. FSCIL lets the system learn that new disease without becoming suddenly terrible at diagnosing the common ones.
Okay, that makes sense. Like adding a new tool to the toolbox without throwing the old ones out.
Exactly.
Yeah.
Or personalization, think recommendation engines. They need to adapt quickly if your tastes change based on just a few clicks.
Without forgetting everything else it knows about you or others?
Precisely. Fraud detection is another big one. New scam patterns emerge. You need to flag them based on maybe just a handful of instances. So it's about making AI more adaptable, more practical in dynamic situations.
Got it. So this paper's trying to push that forward. What's the background here? What led up to this LPDF method they're building on?
Well, the idea of incremental learning itself isn't new. People were thinking about sequential learning, avoiding forgetting, way back in the 80s, like Groisberg, Schlimmer, and Granger.
Right. It's been a long-standing challenge.
A very long-standing challenge. FSCIL kind of sits at the intersection of that older incremental learning work and the more recent boom in few-shot learning from just a few examples.
So LPDF was a step forward in bringing those together.
Yes, a significant one. Its main contribution is how it handles that forgetting problem. It doesn't just rely on storing old examples.
Okay, so what does it do? You mentioned something about synthetic memory.
Yeah, that's a good way to put it. It uses a variational autoencoder, a VAE.
VAE, right. Heard of those? They're like for generating stuff.
Kind of. In this case, the VAE learns a compressed representation. Think of it like a statistical summary of the features from the classes the model has already learned. It maps them to this latent space.
A compressed blueprint, maybe?
A probabilistic blueprint, yeah. Then, when it's learning new classes, the VAE's decoder can generate pseudo features from that blueprint.
So artificial data points that look like the old data.
Essentially, yes. It allows the model to sort of rehearse the old classes using these synthetic features without needing to store all the original data, which saves a lot of memory.
That's pretty clever. Like AI sketching from memory. Is that the only trick?
No, there's another key piece. Prompt tuning.
Prompt tuning.
Yeah.
Like with large language models.
Similar idea, yeah. Instead of retraining large parts of the model for new classes, LPDIF learns these small parameter sets, these prompts.
Okay.
These prompts guide the underlying vision language model, which is usually kept frozen to recognize the new classes. And critically, these prompts are initialized based on previous learning steps.
Ah, so it builds on past knowledge.
Right. And during the training for new classes, the model sees both the few real examples and those pseudo features generated by the VAE.
So it's learning the new stuff while getting reminders of the old stuff.
That's the core idea. It balances learning new things, plasticity, with remembering old things, stability.
Okay, so LPDF uses this VAE in prompt tuning. The original used CLIP as its vision language backbone, you said. Why try swapping it out? What's potentially wrong with CLIP in this context?
Well, CLIP is amazing, no doubt. It learns powerful image-text connections, but it's not perfect. The paper mentions potential issues like feature saturation.
Meaning the feature space gets too crowded?
Sort of, yeah. It might become harder to distinguish subtle differences between similar concepts if everything is packed too tightly. There's also mention of the explaining away problem.
Because?
The model might focus too much on one or two really obvious features in an image and kind of ignore other useful information. So the hypothesis is maybe a different vision language model could offer a more robust or nuanced foundation.
And that's where CLOB comes in. What's different about CLOB?
CLOB, Contrastive Leave One Out Boost, builds on CLIP's ideas but uses a more advanced contrastive learning technique called InfoLo.
InfoLoB, okay. Contrastive learning is about telling similar things from different things, right?
Exactly. InfoLoB is designed to be better at handling the different things, the negative examples, which can help learn a better structured feature space. CLOB also uses ideas from Hopfield networks, aiming for less saturation and more stability.
And the claim is it performs better, particularly in zero-shot tasks.
Yeah, the original CLOB paper showed it often outperforms CLOP in zero-shot classification benchmarks on various datasets.
Okay, so the researchers here thought, let's plug CLOB into LPDIF and see what happens. How did they set up the experiment?
Pretty much. They took the LPDIF framework, kept the VAE and prompt tuning parts, but replaced the CLOP backbone first with CLOP using a ResNet architecture.
Why ResNet? I thought the original LPDIF used a vision transformer.
It did, a VITB16. But for this experiment, likely due to computational constraints and wanting a fair comparison basis for CLIP and CLIO versions readily available with ResNet backbones, they used ResNet 50 and a larger ResNet 50x4 for both CLOP and CLIOB variants.
Okay, so standardized backbones for a fairer fight. Then what?
Then they ran the FSCIL process. They simulated learning incrementally over several sessions, usually starting with a base set of classes and adding new sets of classes in subsequent sessions, each with only a few examples. They tested this on standard datasets like CFAR 100, Mini ImageNet, and CUB 200.
And measured accuracy, presumably, on both old and new classes.
Yes. Tracking accuracy across sessions is key to see how well it learns the new stuff and avoids forgetting the old. They looked at training accuracy, loss, validation accuracy, error rates, the whole picture.
So what was the verdict? Did CLOB boost LPD's performance?
It was interesting and nuanced. With the smaller ResNet 50 backbone, the original LPDIF with CLIP actually edged out the CLOB version slightly.
Oh, really? So CLOB wasn't a magic bullet?
Not necessarily, or at least not universally, but when they switched to the larger ResNet 50x4 backbone, the picture changed. With the bigger model, LPDIF using CLOB started to perform better than the CLRP version in most cases, especially later in the incremental learning process.
So the benefit of CLB seems tied to the capacity of the underlying model.
That's what the results suggest. CLOB's potentially more sophisticated feature representation might need that extra capacity in the ResNet backbone to really shine, which lines up with some findings from the original CLO research, too, about its scalability.
That's a really important finding. It's not just about which model, but also how much power it has. How did this enhanced LPDIF stack up against other FSCIL methods? Did they compare it?
They did. They mentioned comparisons with other state-of-the-art methods like SVT, which uses semantic and visual guidance.
Okay.
Limit, which incorporates meta-learning, and S2C, which uses graph networks. LPDIF, even the original, was already very competitive. These results with CLOB, especially on the larger backbone, suggest there's potential to push performance even further.
So wrapping up the paper's core contribution, it's an empirical study showing that swapping in a more advanced vision language model like CLOB can improve a strong FSCIL method like LPDIF, but the benefit might depend on factors like the architecture size.
Exactly. It highlights that the choice of that foundational vision language model is really critical, and that advances in zero-shot learning can directly benefit incremental learning. It's about finding the right building blocks.
It really shows how interconnected these different areas of ML research are.
Absolutely. Progress in one area often unlocks possibilities in another.
All right, let's shift gears to our Novel Notions segment. Based on this paper and the challenges in FSCIL, what's a potential next step or a new research idea this sparks?
Well, one thing that comes to mind builds on the idea that different vision language models might be better suited for different types of new data. Right now, they pick one model, CLIP or CLOOB, and stick with it.
Okay, so what if you didn't have to stick with just one?
Exactly. Imagine a kind of meta-learning approach. Maybe you could have a system that dynamically selects the best vision language model from a pool CLA, CLOOB, maybe future ones, for each specific incremental learning step.
How would that work based on the new data coming in?
Yeah, perhaps a small selector network could analyze the few-shot examples of the new classes and predict which VL model's embedding space would be let's say, most accommodating or beneficial for integrating those specific classes without messing up the old ones too much.
Huh. So if you get new data that's very fine-grained, maybe it picks one model, but if it's visually very distinct, it picks another.
Something like that. It could draw inspiration from meta-learning ideas, maybe like in the limit paper they mentioned, but apply it to model selection itself. Think back to the medical example. If a new rare disease appears, maybe the system selects a VL model pre-trained on broader biological images to grasp it quickly.
That's a cool idea. Dynamic adaptation of the core model itself. What's another notion?
Another angle relates to those pseudo-features generated by the VAE and LPDIF. Right now, it generates them, and the model uses them for rehearsal.
Right, the synthetic memory.
But how confident are we in those generated features? Some might be better representations of the past than others, especially if the original class had very few examples.
Okay, so some pseudo-features might be noisy or less reliable.
Potentially. So what if we could incorporate uncertainty estimation into that process? Maybe the VAE doesn't just generate features, but also provides a confidence score for each.
And how would you use that score?
You could use it to modulate how much those pseudo-features influence the learning process, particularly the contrastive learning part used by CLOB or CLOB. Pseudo-features with high uncertainty might contribute less to the learning objective when new classes are being added.
Ah, so you downweight the less reliable memories.
Exactly. It could make the replay mechanism more robust, maybe help with the parameter sensitivity issue they noted LPDIF can sometimes have, and potentially reduce forgetting even further by preventing noisy pseudo-features from distorting the learned representations.
Interesting. Using uncertainty to refine the memory replay. Both of those ideas push towards making these systems even more adaptable and robust.
Yeah, they try to address some of the inherent challenges in learning continually from limited changing data.
Well, this has been a fascinating dive into FSCIL in this experimental paper. To recap, the research explored improving the LPDIF method by integrating the CLOB vision language model, finding promising results, particularly with larger architectures.
And it underscores just how vital this area of research is for building AI systems that can actually learn and adapt in the real world, not just in static lab settings.
Absolutely. If you, the listener, want to dig into the nitty-gritty details, we put a link to the paper in the show notes.
It's definitely worth a read if you're interested in the future of adaptable AI.
Thanks for tuning in to Talk Tensors. What's the next frontier beyond just remembering? Perhaps truly understanding and integrating knowledge continuously. Something to think about.
Indeed. The quest for genuine lifelong learning AI continues. Join us next time for another deep dive.